7, you'll be getting an exam, a practice exam. So it'll be half the size of a certification exam, 50 questions. And the idea is that you'll do it during the 2-hour period. So in other words, the real purpose is, how am I doing? Because if you can pass the practice exam, you'll pass the certification exam. So it's basically using the previous PowerPoints that you've got received, as well as some of the questions that you have received during, over the past 10 weeks. Use those as study guides, the PowerPoints and the questions, both question and answer. And so that, so week 11 will be the actual exam, and then week 12, you'll get the answers to the exam and an opportunity to ask any questions about areas you may feel less confident in. So hopefully between those 2 weeks, you'll then go into your scheduled, whenever your exams are scheduled the following week or 2-week period, and be successful. So that's the hope. Fingers crossed that it goes okay. We've tried to cover off most of the need to know: math, hydraulics, disinfection, a little bit of water treatment, sort of the main terminologies, and then the main appurtenances: fire hydrants, valves, meters, pipe materials, and pumps. And then there are a couple of questions around operation and maintenance, construction. So I've blended them together. So it's there's a lot of slides. I'm going to try and minimize them. I've got one cross connection video, and I highly recommend, if you're because there will be some questions on backflow prevention, cross connection control, please go to YouTube. The American Water Works Association has posted some really good videos, short videos, 5, 6, 7 minutes long, about cross connection control. And remember, level 1, level 2 exams are really about recognizing the appurtenance and knowing its application and use. So those types of survey videos are really beneficial. And that goes for water meters and fire hydrants and valves as well, so that when you do the exam, you'll be more comfortable with it. So I hope you take advantage of that. And based on the exam itself, next week, the practice exam, get a real sense of where you're at with respect to writing either a level 1 or level 2. For those of you who are already certified operators at level 1, you know the format. It'll always be multiple choice and only 4 answers. So some of the questions that we've given you during the program on the assignments have been fill in the blanks, which is actually harder because you either know or you don't. Whereas in a multiple choice exam, the right answer is there. It's just a matter of eliminating lesser responses. Either they don't fit, they're for something entirely different, or there's a couple of conditions that don't apply. So you have to basically do a process of elimination to find the right answer. But the good news on a multiple choice exam is the right answer is always there. They're never trying to trip you up by saying none of the above, right? It's always the answer is there. All right, so let's talk a little bit about water main construction. And again, I know that it'll be a very different situation for some of you, depending on the size of your utility, whether you as an operator do construction. This photograph is from the city of Vancouver, where they do a lot of their own pipe replacement, both on the water and the wastewater and drainage side of things. So they have their own processes. I've tried to make this quite generic, but as always, think about the similarities or differences from where you work. So where you work, when a project, whether it's done in-house or by a contractor, people need to know that work is about to start and it's going to affect the water system. So some cities will actually send out notices either a form letter or put a posting on their website or send a text, because some cities use apps that now inform people who subscribe about works that are happening because they want to know for road closures and traffic and that sort of thing. But from the utility perspective, the department that looks after the water system, it's important to have these steps in place. A notification to the residents and businesses that there may be some disruption, and it might be that the city is doing the work at night to minimize that, but they need to still know that. All of the utility companies that have infrastructure in the area, on the street or streets that are going to be impacted, need to be notified, not just for underground service checks, for instance, the one call, but also to know just in case they have plans to do upgrades and the city is planning to go in and do a water main replacement. The next thing you know, the electrical utility is there at the same time. Not very efficient, can cause extra costs to the residents and disruption, and also create problems for the users. Cities will also actually go out before work starts and either video or take pictures of conditions, because some people are very protective of their landscaping or their driveways or properties, and there is an expectation in many places that restoration will happen as close to original condition as possible. And of course, another important step is that there needs to be a survey done, a survey of the grades, the offsets, wherever the water main is going to be going, making sure there's no conflicts with existing utilities, or if there are reserved rights of way that need to be preserved. When a job is ready to go, then and a crew has been assigned, they need to know what equipment they'll be using. It's very common for, say, sanitary sewer or water sewer or drainage projects to need very large equipment, large excavators and multiple tandem trucks. Whereas for a water main project, if it's going to be a shallow project, it may just be a backhoe, rubber tire backhoe, and some of the material might be staged, so they don't need the same number of trucks. Compacting equipment, in other words, when we are disturbing the road base, we need to be able to restore it to its original engineered density so that it'll support traffic. Do we need standby generators if we have to shut down power for any of the work, or if we are using electrical equipment and have to bring our own power supplies to the site? If it's wet conditions, and in this part of the world, they are very often wet conditions, we need to be able to dewater the trench. That's a sample. The picture on the screen is of a typical trench, portable trench dewatering trash pump that can be dumped into the trench as the work is being done in order to keep the pipe dry and the conditions, the material that goes back into the trench suitable for backfill. If we are doing the work at night, do we need lighting systems? And again, up north here, in the winter, days are only 7 hours long. So it's dark at 8 in the morning and it's dark at 4 in the afternoon. So sometimes the lighting systems are required for longer shifts. All things to be considered. Really important for the utility to know what areas will be without water and when, so that both businesses and homeowners can be notified ahead of time. And it's typically standard practice to give customers at least 24 hours notice if possible, if it's a non-emergency, say a tie-in or cutting in a new valve, and it requires dewatering the existing system, isolating the system. Obviously the residents need to know. The fire department also needs to know, and there may be other utilities as well that need to be able to plan around the temporary interruption of service. And wherever you are, there will be different agencies that have different permit requirements, whether that is, for instance, if it's a private company doing the work, they would, even if it's on behalf of the city, that the city has to provide them with permits to occupy a roadway. or to cut into the asphalt, or to even bring, say, a trailer to the job site to be able to store stockpile materials and create a temporary storage area. Crossing a certain classification of gas main may require a permit from the gas utility. Typically, crossing a railroad in Canada requires extra permits from a federal transportation and from the railroad companies as well. Electrical, also now with fiber optics, there may be permits required there, because disrupting or damaging a fiber line can have huge consequences for a city because of the work, the information, the data that's processed through fiber nowadays, and it's just only becoming more so. And even more important, environmental permits. For instance, the city where I worked a few years ago, a lot of sensitive environmental areas based on Indigenous Aboriginal land use pre-settler, pre-colonization that goes back hundreds of years. And if you excavate in certain areas, both the province and the city and the First Nation need to be aware, so that they can either be on site or go in ahead of time to protect the area. So lots of things to consider as a utility about to do construction work. And some of these may also apply even in an emergency. If a water main leaks, some of the steps obviously are planning, and in an emergency you don't do that kind of planning. But there are still permits that may be required and similar steps that need to be taken prior to actually putting a shovel in the ground. So depending on where the work is taking place, pedestrians and vehicular traffic need to be protected. Bicycles, motorcycles could be crossing where pedestrians cross from one side of the street to another, may need personnel dedicated to doing traffic control. And they have to, of course, meet your local requirements for personal protective equipment, PPE, because they are part of your construction crew. Warning signs for vehicles and pedestrians. So really what we're talking about is advance warning. They need to know ahead of reaching the construction site that there may be some work going on and they may have to detour. Cones, barricades, pylons, based on the size of the job and how long you're going to be there. So may, in fact, depending on where the water main is planning to be replaced or installed, the road may have to be closed. Separate temporary pedestrian walkways may need to be created. And there may be signage right on the site of a more permanent or semi-permanent nature to tell people what's happening and where. So when you're actually doing the work, it's really critical that the supervisor on the site and the key staff are aware of other utilities that are buried, whether that's through the use of plans and maps, use of locating pipe. So this is a picture of an M-scope, or what they would call a split box locator, that can actually find underground metal pipe or plastic pipe that has poly pipe that has a tracer wire attached. And the idea is that then the location can be confirmed, marked on either asphalt or gravel or concrete, and then the crew doing the work can expose the line safely and not damage any of the other utilities. And of course, two reasons. One, keep the workers safe from injury. If a gas line is struck, there's a chance of explosion or fire. But it's also about keeping the critical utilities functioning. There have been times when crews have gone out to fix or install a new water main and have broken existing pipe along the way. Not really a positive thing or reputation for the utility if you break more things than you fix. So how to avoid that is accurate drawings and well-trained staff in either using locators, reading drawings, hand digging, and then paying attention when heavy equipment is actually working nearby. So a couple of pictures of prepping, either milling the machine in the middle of the slide is actually milling out the trench. So instead of cutting the trench with a jackhammer and or slab saw, which is on the right, concrete or asphalt saw, you're actually milling out the pavement. And that way the actual surface asphalt can be recycled and either reused on the job or taken and stockpiled somewhere else. Either method, making sure you can see that the person using the saw generates water, which will then generate asphalt millings and slurry. And that needs to be controlled too, especially if it's going into a catch basin that could then go into a creek or to the ocean. It's really important that we're not adding pollutants and contaminants to the receiving waters that are nearby. So either method or any method that's used, some excavators have a large, they call it a pizza wheel. It's just a big saw that rolls, just like if you were cutting a piece of pizza, a pizza pie, rolls across and punctures the asphalt that way. Whatever the method you use, you have to have a plan for dealing with the asphalt that you remove and also any material that comes off the saw. Now, this may be a question on the exam, typically level 2. Width of trench, the second bullet, 0.6 meters plus pipe diameter. So in other words, the prep, cutting the trench, is basically how wide do you have to cut the trench? Add 0.6 meters plus the pipe diameter. So 0.6 meters, it's 2 feet. Say the pipe diameter is 300 millimeter or 1 foot. Basically, then your trench is 3 feet wide. You've got 1 foot that is the pipe, and then basically a foot on either side, 0.6 meters total. Why is that? Well, the narrower the trench, obviously it's more economical in terms of material that has to be removed and either trucked off the site or replaced, but also means for a faster excavation because you're not pulling out the same volume of material. And from a loading perspective, actual forces, hydraulic forces working on the pipe, the narrower the trench, the less load is transferred from surface traffic, say heavy trucks driving on the road, onto the pipe itself. And that becomes really critical if you're using, say, a PVC or high density poly type pipe. You do not want the pipe to be ovaled because of pressure and loading factors from the road surface. Pipe gets inspected, make sure it's good pipe when you accept the pipe either delivered from the supplier directly to the job or it's been stored in your utility yard for some period of time. Make sure there's nothing in the pipe, that a family of cats hasn't made a home in the pipe because it's been sitting in your yard for 2 years. You don't want that as part of the water system. So inspect the pipe for any deformities and also dirt and grit and gravel. And then making sure that if you are deeper than the requirement for shoring, and in this part of the world it's 1.2 meters, 4 feet deep, then you may have to dig your trench differently to allow for a cage or sloping or timber shores. But whatever the case specific to your project, you must make sure that you follow the local safety regulations with regards to the depth of bury, working around equipment, if you're working near above ground utilities, electrical or telephone poles, all of those factors need to be taken into consideration. But really the key here from the exam perspective, keep the trench as narrow as possible. If it's change in direction, either vertical or horizontal, make sure that the pipe is restrained correctly, and the manufacturer will suggest how that happens, whether that's joint restraint or whether it's, say, a concrete thrust block that's poured after the main has been installed. The service, and this will be on the exam, basically recognize what a gooseneck is. So a service tapped off the water main needs to be tapped above spring line. Spring line, if you're looking at a cross section of the pipe, it's above the spring line so that the pipe coming off the main creates what the gooseneck, which allows for both better adhesion and connection to the main, and also making sure that no sediment, if the pipe is tapped too low, it collects in the pipe. Here's a cross section. So on the left, the water main does look like it's been squished a bit. That's not good. But the water main, the corporation stop, recognize that. That'll be on the exam. The corporation stop as opposed to the shutoff at the property line, or the curb stop, sorry, the curb stop here. The corporation stop is attached to the utilities main. This is the gooseneck, this change in elevation at the main. It used to be the old pipe fitters would say, oh, well, we have to put that gooseneck in just in case when we dig up around it later, 20 years later, we don't pull the thing because there's slack. It's not about slack. It's about making sure we create actually a downward pressure. So when you think about the surface, there's pressure pushing down on the gooseneck, and that actually helps push the plastic or copper pipe back into the curb stop. And so makes a better bond, the connection point. So gooseneck, be familiar with what that is, and the difference between the corporation stop and the curb stop, which is typically at or just outside of property. And there may be a water meter at property line. If not, it may be internal to the property in cold weather areas with a shutoff and a pressure regulator, depending on the actual pressure that you're providing to the customers at that point. So, as we mentioned, the water main is tapped above the spring line. So the spring line is basically halfway up the pipe. So it's about 45 degrees above the spring line, right? And then always on the high side. So we do not want to tap at 90 degrees from the invert of the pipe. I didn't mark invert here, but remember that may be on as well. The invert is the inside bottom of the pipe. And that's basically where our survey grades are taken. So we know the actual depth of the new main we're putting in. Water mains are tapped above the spring line, basically as it shows on this slide here. And there's an example of a cast iron water main with a saddle. The main has already been tapped. So a tapping machine would go through there's a corporation stop here. So this nut is removed, the service pipe is removed, and the tapping machine goes through, cuts a hole in the water main. It doesn't have to thread it because the threads happen at the saddle and secures it. And then the tapping machine is removed and the pipe is attached. You can also see on this sketch, there's the tracer wire, so that even though it's a plastic pipe, we can trace it all the way to the property line. But that's a tapping service saddle and the corporation stop. When we're finished with our water main installation, we make sure that underneath this new pipe, if this is a brand new water main, that it's tamped to the spring line. So basically, or sometimes people call that haunching, so that there are no voids underneath the pipe. Voids would allow the pipe to either settle and potentially break. It'll also, any voids underneath the pipe could eventually transfer right to the surface, and then you end up with potholes and collapse and cracking with the asphalt at the surface. So we want to haunch and tamp the pipe all the way down its length to the spring line, properly removing any, eliminating any voids. And once that soil is, or gravel, imported or native, is tamped or compacted, then basically engineers will ask that, depending on the depth, every 150 millimeters to 300 millimeters, the pipe is, or the gravel is compacted in lifts all the way to the surface, and then the surface prepared either for concrete or asphalt, depending on where you're working. And the variety of methods to do that, either with a plate tamper, a jumping jack, Hopac, these are all portable tools, gas powered typically, that can be used by the crew to ensure that the new water main is properly supported and backfilled so that both the pipe and the road, I mean, those are two separate assets, right? We may be installing the water main, but part of our concern is that the roadway, which is also a city asset, is also protected. After that happens, we want to make sure before we tie in the new water main that it is safe to do so. But before we do the bug test, we need to make sure that hydraulically the new water main doesn't have any cracks or poorly connected joints. So we do a test. And the American Water Works Association says always the minimum amount of testing is 50% above the operating pressure. So if you are providing 60 pounds of pressure, minimum would be 50% above. If the pressure is below 100 psi, typically most cities will say we want to test at 150 psi, and for a short amount of time. Could be 1 hour, could be 2 hour, could be 3 hour. The standard at AWWA is typically 2 hours, and that both ensures that the pipe doesn't have any leaks. Sometimes a crew might leave a corporation stop partly on, and so of course the pressure test will fail. Got to dig it up, turn off the corp, and then retest. But there's two parts to the pressure test. One is the pipe wall properly protected, and do you have full integrity of the pipe? And that's not just the pipe wall, but at the joints themselves. And there have been failures. Some pipe, if it gets cracked in shipment or it comes out of the foundry with a flaw, sometimes you don't notice it when you're putting it in the ground. And not only not notice it, it can hold system pressure satisfactorily, but when we bump it up to the higher test pressure, it fails. We need to know that before it becomes part of the water system. The other part of a pressure test is what is the allowable leakage? And the American Water Works says that you can count up the number of joints in a section of new water main based on pipe diameter, and then leakage is calculated in very small amounts, half a liter, something like that, depending on the length and the diameter of the pipe, basically dependent on the total volume of water inside that pipeline. But there are allowable small amounts of leakage. Typically it's a gasket getting pushed slightly or moved requires a little bit of extra water to fill that space, but the pipe's not leaking. So we need to calculate that. So the testing contractors will have those formulas or the utility. And so what they'll do is they'll pump up the pipe to the specified level, turn off the pump, hold it, and then have a basin of makeup water and measure how much of that is needed to keep the pressure at its desired level. And then the pipe either passes or fails. If it passes, it can now be bug tested and disinfected and then eventually tied in. So disinfection is always per American Water Works Standard C651. And remember, when we talked about disinfection, we talked about contact time. And contact time is how long is the disinfection product, in this case, say, sodium hypochlorite, how long is it in contact with the pipe before it may be moved on to where the customers are. And that determines the longer the contact time, the lower the concentration of disinfection we need. If we have to move it, say in an emergency repair, and we need to restore water service within 15 minutes, then our concentration must be much higher, say 200 parts per million. If we have 24 hours, maybe down to 25. So it's in the standard, and depending on what your practices are, that's how basically you set up the disinfection. And typically the standard allows for 3 different methods. Solid calcium hypochlorite, they're like big pills that can be put into the water main as it's installed. And then as water is added for the pressure test, they dissolve and make contact with the pipe wall and the joints and so on. So typically 24 hours, we got a dosage only of 25 milligrams per liter. If we are doing what's called the continuous method, and that means we're going to inject typically sodium hypochlorite from one end of the pipeline to the other, then we need to dose it so that after 24 hours, there's not less than 10 milligrams per liter. And the slug method, that is basically the example I gave before. The lower contact time, we want to boost the concentration. So remember, concentration is the dosage of, say, chlorine, calcium hypochlorite, sodium hypochlorite, and the contact time is how long do we have where that disinfection agent is working. The longer the contact time, the lower the dosage required. And then after that happens, we can then flush the system out according to your procedures so that you don't have chlorinated water dumping into, say, a sensitive environment. And now we can talk about tying into the water main. So we flush so that basically we want those chlorine levels equal or below slightly the local supply. So typically no more than 2 milligrams per liter. And then what we do is we take those samples into the lab. If you have that procedure, making sure that the water is safe. Because as soon as it's tied in, it is now part of the live water system. All right, let's talk a little bit about maintenance. And we're going to cover off a couple of maintenance programs, and I'll highlight the types of questions that may be on the exam. And again, when I say maybe, they show up on some exams, not on others, right? They have a huge database of questions. So we'll talk about why maintenance is important and some example programs that typically have questions on the certification test, and then a little bit about cross-connection control. So, I mean, this is pretty basic. Proper maintenance practices significantly reduce both our long and short-term costs and system downtime and risk of contaminated water. So just expand on all of those. Long-term costs are not the costs of today, but overall, all of you as operators have joined your utility at some point in its life. The utility may be fairly young, been around for 25 years, or in some cases, it could be 200 years old. So we've all inherited what is in the ground, what are pumps and motors, everything, every part of the system. And it needs to be maintained in order to provide the customers with safe drinking water in the quantities that and the volumes that they expect and need. So we don't throw all our eggs into one basket and then it fails 2 weeks from now. We need to plan for the long term, and typically then managers and engineers look at operational and capital budgets in order to do that. What do I need to do this year? And I set up my programs, and we'll look at a couple of programs that are typical in maintaining a water system, certainly not exhaustive, but typical. So we have to plan out what that costs. And so, because if we're going to ask our customers to pay for that through either their water meter charges, the volume of water use, or through separate permits or parcel taxes, how much do we ask from them? We need to ask enough so that we can do our short-term, day-to-day, 365 days of the year, cover all of the labor and the equipment, the trucks and the tools, any permits, any chemicals, all of that needs to be covered in the short term. But some monies need to be set aside for long term. And not just long-term replacement, because that's capital, but long-term maintenance. There may be larger maintenance programs that need to happen. And so we have to budget for that. And so our operational budgets are created based on that. And sometimes it looks like, well, we've just taken what we had in the budget in 2020 and we'll just roll it forward to 2021. Happens all the time. And quite often that's good enough because in theory, the money we had last year was enough to do both the long-term reserve and planning and also the short term. But however, If we don't do any planning, our short-term costs continue to go up. And we see that evidence of that, say, for instance, in the number of breaks or bursts. If those continue to go up, it could be because our pipe has reached the end of its useful life, or the services are near the end of their useful life, or a pump is continuing to fail. What that means is it takes more maintenance dollars, labor, equipment, and material to keep it working like it was new. Whereas when it was new, once it was installed, we didn't spend any money on it. So we have to be able to plan what we call a life cycle. And how long do our assets last? Well, different assets have different life expectancy. Depending on the type of material used, a water main might last 100 years. The water service, if it's copper, might only last 40 years. And if we have 10,000 of those, we now have to figure out, well, how many of those are going to fail? Because we cannot afford to replace 10,000 all in the same year. How many can we replace? 200, 100, 50? It all depends on how old the system is when we're working on it. Are there any reserves? And have our engineers planned for a replacement? The American Water Works Association says it would be really ideal if every water utility in the world could take 1% of its assets and replace them every year. 2% would be even better. But a 1% replacement rate for long term would mean that we're taking, the system will last 100 years. And we're going to replace, say, the water main on Main Street today. Well, we won't need to do it for 100 years because we've got all the other years, 99 years, to do the same thing elsewhere in our city. And it's the same philosophy, whether it's a large city, small city, rural, or urban. The problem is a lot of our water mains were installed in batches or bunches, where a whole subdivision was installed in the same year. And now that represents 5% of our whole infrastructure. Well, chances are it'll all start to fail at about the same time. So our planning has to take all of that into consideration. This is why choosing the right material, the right for our mains and our services, and having standards that reflect the best practices, say the American Water Works Association, and training our operators so that they know how to maintain each asset so that it will last the appropriate amount of time. And, as an example, when I was in North Vancouver 40 years ago, there was a type of pipe, an asbestos cement pipe, that had been installed in the 1960s. And it was supposed to last 60 years. But because of the geographic layout, the topography in North Vancouver with very steep hills, parts of that water system were operating at extremely high pressures. And the asbestos pipe that was chosen was of a thinner pipe wall. It could not handle the fluctuations from very, at high demand time to extremely low demand where the pressure would build up. So after 30 years, that pipe started to fail. Well, the city did not expect to have to replace that pipe so soon. So it had to borrow from what was called a reserve to replace that pipe. The new pipe that went in was properly spec'd and should last 100 years or 80 years. But that kind of planning is necessary to ensure that the system is still working long after you retire. And again, one of the measures of that is what are your short-term costs comparative year over year? And if they are increasing, typically it means that the infrastructure, the assets, are depreciating and failing faster than your replacement program. So that needs to be tweaked. One of the key issues, why is that so important? Well, system downtime becomes a huge issue. The interruption of supply. And if pumps fail or reservoirs cannot keep the water in them because of leakage, then our customers are not getting reliable supply. The other piece of not getting reliable supply means you potentially have health effects, impacts, either because the grade line crashes and you potentially allow contaminants in, or the actual practices allow things like backflow to happen in the system, or the number of breaks allows non-potable water, contaminated water potentially back into the system. So preventive maintenance versus repair maintenance or short-term maintenance becomes really critical. So preventive maintenance is planned. We plan these programs out through the course of a year or a season. One of the reasons we can do that is if we have these plans already operational and our staff are trained and we have the right equipment, we can now count on over time there being fewer failures and breakdowns, fewer emergencies being called in the middle of the night to deal with a problem, an issue in the water system. Corrective maintenance, on the other hand, sometimes called repair maintenance, it's really not maintenance at all. It's an emergency response because a pipe has failed, a pipe has burst, a service has blown out, a fire hydrant has been hit by a car. These tend to be more expensive. Things that can be attributed to something like a car hitting a fire hydrant, okay, that's not a reflection of maintenance programming. But corrosion in steel pipe or failures because valves are freezing and will not turn, those are typically good examples of short-term maintenance that hasn't been done properly. So if you have a lot of valves in your water system that are either buried or missing, or the operating nuts don't function, or it seizes up, that points to a gap in preventive maintenance. And of course, how that shows is when you need the valve to work, it won't. And that comes at a cost as well. And not just a financial cost, but also a cost of reputation and credibility of the utility. Bottom line is, every failure we have that's of an emergent nature costs more, and the more it costs means there's less other preventive maintenance work that can happen. And I've had to deal with a water main break. A typical burst might cost $1,000 to fix. But sometimes if it goes really wrong, it could be $10,000 or $20,000 to repair, and not to mention the damage to private property. Well, that can then impact your ability to do preventive maintenance because you have to use so many resources to do that. So let's talk about a couple of programs, and it's going to vary. I want to highlight a couple of things that'll be on the exam over the next few slides. But one of the issues around preventive maintenance programs is they have to fit your utility. The American Water Works, as kind of a blanket organization, has a very simple philosophy, and it's one that really works well. And it comes back to operators. Know your system, understand your system. As I'm talking, I'm hoping that you think about your own utility. What are the weak spots in the utility as far as maintenance are concerned? Are there areas in the water system, in the water network, that nobody wants to go? Nobody wants to touch a valve or turn a hydrant because there's a real fear that it won't work. That if I take the valve cover off a valve box and put a key down to operate a valve, that it'll break. So if you know that, that suggests that there's parts of the system that do need attention. And the response is that's the one where you should be going. However, easier said than done. It may require, at certain stages, if it goes too far, it may require a capital program. You might have to replace the entire valve. A municipality, I don't know if I told you this during the fire hydrant discussion, but not too far from where I live, a small city was doing the right thing and replacing all their fire hydrants. The ones that were 60, 70 years old, they couldn't get spare parts for. And they knew that if they didn't replace the fire hydrant, they wouldn't be able to service it. And boy, that would be a terrible situation if there were a fire and the fire department attached their hose to the hydrant and it didn't work. So they did the right thing. They went to their council and asked for extra money to replace 10 fire hydrants every year. And they had about 500 that needed replaced. So it's going to be a multi-year program. And so they went out, got the new fire hydrants. They were approved, good quality fire hydrant. Their crew went out to dig to replace the fire hydrant. And as they were digging, they were cutting the old fire hydrant off to put the new fire hydrant onto the leg, onto the spool piece that connected the valve off the main to the hydrant. So they were cutting the old one and lifting it out with a crane, and the two pieces of pipe connected, stuck, and pulled, and it popped the pipe that was connected to the big main. It pulled it out and the valve that was holding back all the system water pressure. So the 6-inch valve pops off just like a cork, and now the hole is filling up, and it is filling up and filling up, and it doesn't take long for a full 6-inch pipe at 120 psi. Boom, floods. Now it starts to go into people's houses. And this was a week before Christmas. And in this part of the world, that's cold. There's ice. There's potentially snow. There wasn't snow at the time. So they go to shut off the valves. So they shut one valve off, didn't make any difference. Shut the other valve off, didn't make any difference. So the main that the hydrant is connected to is spilling and flooding this street. So they go back further. Still didn't work. So something's wrong. It took them 6 hours to isolate that main. And what they found was that the valves on the big 18-inch, so 450 diameter asbestos cement main, had actually a reverse thread. So typically in the American Waterworks world, when you are turning a pipe, a valve key clockwise, you're shutting a valve down. These were right-handed. So they were actually opening. And what they found was 2 of the valves that were critical were shut. They still had water because it was a one-way supply, right? It was restricted. So when they went to shut the main off to isolate it to prevent the flooding, they actually opened up the valve. So it took a long time to figure it out. It was an old superintendent that actually finally arrived, figured it out, closed the water. By that time, 10 houses were badly flooded. And those people had to leave their houses. It was so bad. It cost hundreds of thousands of dollars in insurance claims. But the real issue wasn't that the city shouldn't have done the hydrant replacement, because it was in need of replacement. What they hadn't done was check the valves on either side of the hydrant T. One, they were not the asset that they thought. They were right-hand thread and right-hand thread instead of left-hand. And 2 of them were closed, which meant the system wasn't really optimized for fire protection. So a good example of knowing your system. How does it work? And have we done enough maintenance to keep it in its optimal shape? So leak detection is one of those things where a lot of cities in this part of the world, because water is cheap, and I think I've mentioned that before, in this part of Canada, we don't really pay for water. We pay for the pipe and the valves and the pumps. And there's lots of water. So we typically wait until a bit of water shows up on the road, and then we go and look for the leak. But a proper leak detection program means not waiting for those water leaks to happen where they can become visible, but actually looking for potential leaks before they show up. In other words, depending on the depth of the water main and the type of soil surrounding that pipe, water might never show up. And so how do we know that the system is operating correctly? Well, we typically do an audit. How much water are we buying or producing from a treatment plant? Subtract how much we sell. What else do we use water for? Well, it could be flushing. It could be filling up trucks for the parks department or swimming pools or things like that. Okay, figure all that out. Where's the leftover water? Is there any? And in North America, the average is potentially up to 30–35% of water does not make it to the customer, either through leaks or inaccurate meters. And in other parts of the world, South Africa, South America, South Asia, it can be 60–70%. It may be that high where you are as well, because of older infrastructure and also the fact that our meters might not be accurate. So think about producing 10 liters of water and the cost to do that, and only 5 liters makes it to the customer who pays for that. So the utility is actually losing money. You know, not many oil companies would survive if you went to get gas for your car and only had to pay for half of what went into the tank. So with water systems, the seriousness with which they take leak detection depends on the cost of water and the age of their infrastructure. In the 1980s, Britain was going through, in the UK, some serious issues and crises around their water rates. And the government chose a course of action that personally I don't agree with, but they privatized a lot of the water systems. So they made them for profit with shareholders and so on. But what they did as a result of that, because now there's a shareholder that wants a good return on his or her investment, they pumped a lot of money into finding leaks. These were old water systems, and the public utility did not have the means to raise taxes or utility rates enough to fix all the pipe. But the private sector did, and they did that. So a lot of the leak detection techniques and equipment come from those efforts to improve how we find leaks, and can we find them before they show up and not cost us as much money. So you're going to see a couple of examples, and typically leak detection means listening for water, because as water escapes under pressure from a pipe, it makes a noise and at a certain frequency, and that frequency changes based on the type of pipe material: copper, asbestos, cement, or PVC. So we can use basic equipment like an aquaphone or a geophone. Geophone just looks like a doctor's stethoscope with two, actually, let's bring it up on, should be able to bring it up on. Geophones. Let's see if we can find them. So here's a couple of examples. Some of the older style geophones are basically just two, there we go. These are the famous ones. You can see two discs, and they're actually cut like sandwiches with rubber tubing into your earpieces, and you actually listen to the sound of escaping water under the road. And these are quite popular still. Now, you can imagine going from block to block in a city or town. That's not a very efficient way to do it. So typically these kinds of tools, listening devices, are used when you know there is a leak close by. So typically we would do leak detection in an area where, say, 6 city blocks. Our SCADA system shows that we're, oh, I haven't shared the screen, did I? There, so this is the Pollard water geophone. Sorry about that. Here I am talking without sharing it. So this kind of a device you wouldn't use unless you knew there was a leak close by, as opposed to correlator. As opposed to something like this, where you put something on one valve and then on the other, and basically bring the wires through. Can be done either direct wire connections or Wi-Fi to the wire, and it's basically how much time does the signal take to find the leak and come back. And it compares the two devices and says, okay, the leak is here. Now, it doesn't know it's a leak, it just hears noise. And this is a very popular one. These two sensors go, the transducers go on one valve to the other, and then they transmit through Bluetooth to the receiver. And it will say, okay, there is a noise 30 meters away from transducer A. Now that noise might not be a leak. It could be a leak. It could also just be where there's a service connected. So you want to make sure no one's using water there. If there's still a sound, probably is a leak. Now, once you've found that location, then you would go to the geophone and use the geophone above that spot to know exactly where your crew is going to dig. So there's lots of good equipment out there to help you, the utility, find the leak long before the water actually shows up. And it could be long before the homeowner, the property owner, actually even hears the leak, which is good, because if you can hear it, then you know it's getting worse and maybe a problem. So the equipment can be quite sophisticated, like the GeoScan, the one I just showed you with the transducers. There are many American cities now using those permanently. They leave the transducer on the valve, especially in downtown high traffic areas. And they tell them to wake up in the middle of the night when there's not as much traffic and not as much water use, and listen. And then once a week, someone will download all of the data and then run a profile and say, is this a leak? Because it's also expensive to dig in some of the built up metropolitan areas in some of the big cities. So you don't want to dig unless you have to, but you certainly don't want to wait until a leak has become major enough that it's going to disrupt traffic, isolate the system, put people out of water, and so on. But a lot of those big American cities, for example, and Canadian cities, those water mains are coming on 100 years old. So there will be leakage. You want to find it before it becomes a problem. So that's the difference with a preventive maintenance program, is using this type of equipment before someone phones and says there's been a burst. Then you are reacting, right? So they don't need to be very sophisticated. It could be some of the leak detection methods that are still being used. It looks like a telephone earpiece with a metal bar through it that you would put onto a fire hydrant or on a gate key and listen. And if you can hear the sound of water escaping, you can then track it down. Not a very efficient way to go through a whole city, but it is good to pinpoint. The other equipment, the correlator and the data loggers, are basically for doing profiles of city to see, are there leaks? And there may not be. So we don't have to do anything further. But if we pick up the sound of a leak, now we try and pinpoint it so that we can actually repair it. So here's an example of what's called an aquascope. So similar to a geophone, and it's basically a handheld transmitter, a receiver, and basically a wand with a cup for solid surfaces like concrete or paving stones and so on. And it basically will pick up any noise. And you tell the piece of equipment what type of water main you're standing over. Is it cast iron? Is it steel? Is it ductile? Is it AC? And that way it will pick up the frequencies that those leaks through those types of pipe create. It helps you find the leak long before water starts to bubble up through the cracks in the road. So that's good, because then you can do that repair. So if you don't, and you wait for the burst to show, now we are doing what we call short-term or repair corrective maintenance when a pipe bursts. And cities should be tracking how many of these bursts they're having every year and on what type of pipe, so that the utility can do an analysis and determine, is there a certain type of pipe that's failing? How old is that pipe? Because if the pipe is now, like the example I gave before, 100 years old, we can expect more breaks. If the pipe is newer, is it because of the operating pressure? Is it because of other factors that we can try and analyze to prevent the breaks? Now, you might be asked about a cylindrical break, and that is a cross or a beam break across the back of, or the circumference of the pipe. So the pipe basically cracks because of a pressure point underneath it, or load, and so it splits perpendicular to the pipe itself. Typically on cast iron, but it happens on AC as well. The other type of break is a longitudinal break, or a split that can go from joint to joint. Very common for PVC or asbestos cement, or cast iron, especially if, say, there's been water hammer. If there's been a pressure surge because of a power failure, or because someone shut a valve too quickly, it could split the pipe lengthwise, and now the whole pipe needs to be replaced. A pinhole typically is a corrosion hole. So we're looking for things like, so a pinhole is typically associated with a steel pipe. It could be corrosion through a reinforced concrete pipe as well. And then blowouts are massive failures, and that's typically on an AC type of pipe. And those can occur naturally. And with asbestos cement pipe, there's a narrower, thinner wall at each coupling. This is the way the pipe was designed. And if there's any pressure surge, two rubbers that are inside the collar, one of them might herniate, and water will start to escape under pressure. And it's just like a knife. And slowly it etches the pipe wall until the pipe gives out. And when it does, it typically blows out a whole side of the water main. And you may have experienced that if you have AC in your system. So that would be a blowout. Makes a very expensive repair because it does a lot of damage. It's a full escapement of water that needs to be isolated. You can't fix that under pressure. It needs to be, the main needs to be completely shut down. Typically a lot of road base or surrounding material is lost. And typically a lot of that material goes in part of the pipe. And now it has to be removed, and that becomes a real problem for some utilities. And with the old cast iron, you may have lead joints that slowly work the lead as a bead, pushes out of the bell, and then water escapes, and the lead needs to be pounded back in. But the good news with those kind of breaks is you don't have to shut the water main down. You just use chisels and a hammer and push the lead back into the main to stop the leak. So it all depends on the type of pipe you have in your system to know how to fix it. But here's the thing, for a utility, knowing your system means knowing what kind of pipe you have and its diameter, so that you have the right parts and tools and materials to make a repair. In this part of the world, it's not unusual to have 30 bursts over a 12-month period. But those typically are on much smaller diameter pipes, say 100 millimeter and 150 millimeter pipe, and typically broken back cylindrical cracks on cast iron. So a repair clamp, a two-piece repair clamp, can be fit over the pipe. The pipe is cleaned, the repair clamp is put on, and the leak is stopped. So that can be quite beneficial because it's not an expensive repair, as opposed to having to cut out the entire length of the pipe to make that repair, and then use the two couplings. And the couplings have to be the right end diameters to see if we can find an example. So as an example, here are the repair clamps that can be fit over say a broken back, a cylindrical crack on a pipe. Would be this type of repair, and this coupling you would use because it's got an outlet for service. But if you're actually going to couple the pipe together, then you will need, instead of a repair clamp, these are different styles of repair clamps, you'll actually need a coupling. Let's see if we can find the couplings instead of the repair clamps. Repair clamps and saddles. Yeah, let's go Okay. We'll find you a repair coupling instead if you have to replace. Then you probably recognize these when they pop up here, if they pop up here. So this kind of a repair coupling. So 2 of these and a new piece of pipe and can be added and basically dropped in between to replace the damaged section. But you need to know what's called the outside diameter of the pipe. So it has to match, because steel is a much thinner and smaller outside diameter than cast iron or asbestos cement. So you need to stock the right clamps. Do you want it to come with restraint? Do you want it to basically be cast iron, or do you want it epoxy? So a variety of models, and there's several repair coupling companies that operate. But if you have to isolate a section of main, then that's the type of product you would use. So you can see the different types. Some are slide on, so you don't actually carry them, they have their own handle. And you can see instead of 4 or multiple bolts, they only have the one, like a Victaulic coupling, and you can actually slide it over the old pipe. So there's lots of innovation in how to do it. But the bottom line is, it is still an expensive repair compared to a 2-piece repair clamp. If it blowout from an end of a main, then you would put a cap on it. Or again, if you've leaded, let's see if we can find that. That doesn't happen as much anymore, but so the old lead pipes, yeah, we'll probably not see them here, but you can have lead come out of the joint, and so you have to hammer it back in. There's a cutaway of a rubber joint, but on cast iron pipe, you would then punch the lead back into that gap. And that is not expensive relative to a pipe blowout, but you do need the specialized tools. Again, I didn't share it with you, so here's an example of like a joint. So a leading iron would push the lead back into this gap here. You can see lead is here. The hemp, which stops the lead from running into the water main, was put in first. And then lead was poured in. And after 50 years, sometimes the lead gets pushed back out and actually sticks out of the main, and then water, the yarn can't stop the water, so it blows out. So you basically take a chisel and punch the lead back into place. So it's not an expensive repair compared to having put in an entire length of pipe, but it's still expensive relative to the disruption that could happen to your customers. So quickly typing something here. Okay, let's just carry on with this. So we've talked under the hydraulics about positive pressure. So remember, positive pressure means that as long as there is some pressure, some head in the water main, then pathogens can't get in. So when we're talking about positive pressure when we're repairing a water main, if it's a crack or a spray out from a leaded joint or a pinhole, we can make the repair without having to turn off the water and having to isolate a section of water main. So that's beneficial. So there are less health risks with those kinds of repairs. However, if a whole blowout happens and we have to cut out a section of pipe, we have no choice but to isolate the main. In that case, if we do, the recommendation is that you make sure that the new pipe and couplings are clean. Some utilities insist that you spray bleach or hypochlorite on them and or in the main, and that you flush then the water main before it's back in service. Some utilities actually, after they put the pipe back together, tightened up the bolts, loaded up the main, they flush it through a fire hydrant so that you don't build up that contaminated or potentially contaminated water in the supply, and take a water sample. Reality is people will be using the water, but if there is a problem, the utility will know within 2 hours. The presumptive preliminary results will say if there's a problem or not. And that way the city can return and either re-disinfect or continue to flush to minimize contaminants. But it's important that whatever practices you have in your utility, you minimize non-potable water getting into the pipe when you're doing the excavation and repair work, and then flushing the main and ensuring that it's backfilled properly before you should also keep a record of that break, the type of pipe, its size, the type of failure, if there were pictures taken. Some of the maintenance management or asset management programs that are used now allow the site supervisor to attach separate files. So it could be photographs, it could be sample results coming back, and they can all be attached in the same folder so that the utility knows exactly what happened when, and of course over a 12-month period can, when they're building their budget for the next year, determine what steps need to be taken, if any. Is there a section of water main that needs replaced, or what else do we need to do? So the record keeping becomes important. All right, so one of the big main, and from an operator perspective, I hope some of you have participated in flushing programs as operators, because there is, if it's done correctly, the flushing of a water system is an amazingly thorough way for an operator to learn about how their water system operates. Because if you're doing it right, you're looking at the source, you're looking at the outlying areas, you know where the valves are that need to be turned, the fire hydrants, the blow-offs, your operating system pressure, the sensitive areas in the system, and you get a real good snapshot overview of how the system is performing. Okay, so why do we flush? Depends. The American Water Works Association says, well, you better figure out, what are you trying to do when you flush? Are you simply turning over a little bit of the volume? Are you trying to raise the residual, the chlorine residual, from a low level to a higher level? Are you removing sediment? Are you trying to take biofilm, say from C900 PVC pipe or AC pipe? Is it taste and odor issues from the customers? What is it that you're trying to correct? And know that first, because that will determine how you flush and how much of the system you flush. There are small cities that flush the entire system, and they start by draining a reservoir and using the water out of the reservoir to flush, and then they clean the reservoir, put fresh water in the reservoir, and their system has been renewed. Most cities don't have that advantage, so they'll compartmentalize, break the system into separate subzones, either through closing valves temporarily or changing the supply on pressure regulated feeds, and then start always at the source and move to the outlying areas. And so it becomes a systematic program. Make sure too that you know the difference between, say, a conventional flushing program, which is simply going to the fire hydrant, like you see in the picture, turning it on and waiting for the water to clear. Nothing wrong with that if that's in response to a specific, say, complaint of dirty water or taste from a resident, say from the house right behind the fire hydrant. But a unidirectional flushing program means that we're now looking at directing all of the flow along a single line And to do that, we have to close the branch valve. Well, we need to know where those valves are. We need to know, are they accessible and do they work? When I put a key on the valve, will it turn? So that becomes the basis of a unidirectional flush. And we move through the system or a portion of the system, always bringing clean water into an area that needs to be flushed. The other thing is you can be moving high volumes of water at high velocities. Well, it needs to be dealt with. You don't want to cause flooding problems to your customers. You also don't want any measurable chlorine going into a fish-bearing stream or ocean or lake. So what steps are you going to take to either hold the water back or dechlorinate it as it's going into the environment? This may be on the exam. Scouring velocity. So we're looking at 0.75 meters per second minimum, anywhere from 0.75 all the way up to 1.5 meters per second. In other words, remember the hydraulics, right? When we speed up, when we create a demand, say turning on a fire hydrant, that speeds up the water, the pressure drops. So that's fine. What we need to do though is either through our SCADA system or from pressure gauges on other fire hydrants in the immediate area, how far does the pressure drop? Because if it drops below 20 psi, well, 140 kPa, we could be putting people out of water. So again, how well do you know your system and how well will it perform? So when we set up our flushing program, it's typically either looking at drawings or going through our SCADA system to determine our pressure profile and gradients so that we can get the velocity sufficiently high to actually clean the main. Remember, hydraulically, head loss is friction loss. So by scouring, what we want is all of that water flow against the pipe wall, and that scrapes up barnacles, iron bacteria, or even biofilm. And we need even higher velocities for biofilm. And that's good. Okay, but the other part of that is so we create that velocity, that demand, by opening up a fire hydrant. The other part of that is when we open up that fire hydrant, how much will the grade line drop and where are we going to dump the water? And then how long will it take to clean that section of pipe? Well, you need to know how long is that section of pipe? What is the pipe diameter? The larger the pipe diameter, we're going to have to open up multiple fire hydrants or the fire port, the pumper port instead of the side port in order to get the velocity. Because if you don't open up enough demand, the grade line won't drop. You will not get that velocity. You have to create demand. And so for operators doing flushing program, one of the things I found over the years is they tend to overestimate how much water is coming out of the water main when it's really not flowing. You know, say a 150 diameter water main, you've got to pull 500 gallons a minute through the side port or the pumper port to get that 0.75 meters per second. That's a lot of water. So either measure it with a pitot gauge or flow meter somehow, or off your SCADA system, but you need to get that flow. If it's a 100 millimeter main, it may only be 250 gallons a minute. So you're basically doubling it if you're going to flush a 6-inch main. And if you're at a 200 or an 8-inch main, you now have to basically pull 800 to 900 gallons a minute through the hydrant. Now you kind of have to use the pumper port. So if you're not doing that, yes, you're moving water, but you're not scouring. Okay, well, if your goal is just simply to turn over the water, you don't need to scour. So it comes back to what I said. Why are you flushing in the first place? If you're flushing to improve the residual and remove sediment, you need scouring velocity. If you're just simply trying to do an exchange of volume to improve customer or minimize customer complaints, you can just keep a slow flow coming out of a side port on a hydrant, and it'll take longer, but you'll still have the same result. So flushing always based on what you're trying to accomplish. So the plan is figure out what you need to do. Flush at night, especially if it's in a built-up area. Ensure that your area is well lit, and then look at your drawings. What mains are you flushing? Where are your exit points? And what valves do you need to turn to do that? Again, you're moving from clean to dirty or unflushed areas, and you don't want to go back in a circle and bring clean water into an area and then push dirty water back to an area you've already cleaned. This is why you have to turn valves. Start near the source, flush towards the outlying areas. Make sure you have adequate volumes. And again, that's what the pressure gauge is for. You don't want to put people out of water. You can warn them that the water might be discolored or there might be lower pressure, but you do not want to go negative. Open the hydrant or blow off slowly because you don't want to create a hammer situation. You may take a sample for chlorine. Some utilities actually will do a bacteriological sample when they're finished too, and measure things like turbidity or color. Again, depends on what you're trying to do with the flushing program. And of course, record keeping, it becomes really important. So some utilities will do all of the system every year, others portions of the system. So your records will tell you, and your water sample results will tell you, do we have low residual? Do we have taste and odor issues? Do we have turbidity spikes? Based on that, you plan the flushing program. But as I said at the outset, as an operator, it's one of the best ways to get to know how your water system works if you are part of the flushing program. If you're turning valves, you're inspecting the valves at that time and their condition. If you are putting pressure gauges on hydrant, you get to learn the hydraulic capacity of your system. If you are draining a reservoir and then cleaning it as part of it, that part of the system. So it's a real great way for operators to know how their system functions. And then you measure the results and plan for the next year. And both AWWA and a lot of the regional waterworks associations have great information on flushing program. That's an easy one to Google, and you may find some PDF documents on how unidirectional flushes are done in different cities and how to set it up on a map, depending on how your maps are set up in the first place. If you can't get scouring velocity and your system is AC and C900, and you're trying to remove biofilm, you may go to swabbing. Sometimes people call it pigging, but they're really two different things. A swab is a soft-sided, basically sponge that goes inside a water main and is pushed through. When you open up a fire hydrant, it pushes itself through and cleans the main. It pushes the debris out ahead of it. A pig has got a harder surface and can actually scrape iron bacteria out. So you don't really want to use a pig on AC or even plastic. You would use a swab for that. And here's an example. So there's swabs, different sizes. And typically, if you are swabbing, say a 150 main, then you would use a 200 diameter swab. And you would push it in through a fire hydrant, compression hydrant, and here it is coming out. You can just, I think, barely see it. And it pushes the dirty water out ahead of it. And typically they're put in trains, multiple swabs, and so you have to remember how many you put in because you want to get them all out. And like a flushing program, you would control the valving so that you can move the swab based on the demand. You turn on the fire hydrant, and wherever you put the swab in, you tell customers, don't use any water because we don't want to trick the swab into making a left turn. We want it to come out the exit point. And so it's basically flushing one step higher because you're actually using a device, an appurtenance inside the main. So we typically soak these in bleach, and we can take the top off the fire hydrant. If it's a compression fire hydrant, we can actually flush right through it. And we launch and retrieve our swabs or pigs through the hydrants, which is very versatile. City of Richmond, not far from here, on the mainland, because it's all AC and C900, never does a regular flushing program. They have built in that every 3 years they'll swab, and that removes the biofilm. You don't have to worry about dumping a ton of water because you're really just moving the water in the column ahead of the swab, because as soon as the swab is removed, You slowly isolate the main and move on to the next location. So you use a lot less water. But remember, it always comes down to what is it you're trying to accomplish in the first place? What's your goal? Now, in terms of proactive maintenance, one of the key things is rehabilitation of water mains. And we don't have time to go through all of them, but back in the 1920s and 30s, cement mortar lining was put into cast iron and then eventually ductile because it was a much better lining material for water quality purposes. And they developed a cement mortar lining method of replacing the lining without taking the main out. So main is isolated, entry point is cut in, kind of like cutting in a section of new water main, and a retrieval point, and a two-part basically cement coating is pulled through the water main. So it's basically a hose is dragged through the water main, it turns and spits out a loose, light cement. And then a trowel follows it and applies it to the wall of the pipe. What that does is the pipe's been cleaned and scraped, and now we're putting a fresh coating on so we don't have to replace the water main. After cement mortar relining became popular, companies developed an epoxy that does the same thing. And here, let's just quickly, I'm going to find you a picture of epoxy water main. Because think about the cost of digging up a new water main or an old water main and putting a new one in. By doing a epoxy or cement mortar lining, we can do that inside the ground. We don't have to remove the pipe, and basically allows us to renew the pipe without, here's a spray in place. So the pipe is cut and cleaned. Here's a method that actually uses a folded lining. So there's slip lining, and then it's popped into place inside. So it becomes a pipe within a pipe. Here's the problem with epoxy. If the epoxy nozzle stops, it fills the pipe with epoxy. That's not good. But that's basically what happens when you spray on epoxy inside the pipe. It's a very thin, so it's actually thinner than cement mortar lining. And here's an example of before and after. So instead of having to dig up and replace all of that water main, the pipe is scraped clean, and then the epoxy is pulled through the water main and sprayed on, and then once it cures, you've basically got a brand new pipe. This is assuming that the pipe wall itself is okay, and then you don't have to dig it up. So there are a variety of techniques used to do that, and all fits under the category of rehabilitation. So instead of digging this entire pipe up, we can create a new pipe inside the old one. So that's basically what we're talking about when we talk about rehabilitation of pipelines. But that's planned. That's not an emergency response. That's a planned replacement of the asset, and typically falls under what we call trenchless technology. But it can minimize disruption because you're not digging up the whole street, and you're extending the life. The pipe might be 60 years old. Well, now you've just added 40 years to it instead of having to dig it up and replace it. And this is an example of a cement mortar. So this was the pipe before. They scraped clear, got all the barnacles, tuberculation. Remember on the exam, these iron bacteria nodules that build up on the inside are called tubercles, right? Tuberculation. Scraped out, and now we have a cement mortar that's put in and cured. The difference with the cement mortar lining is if you pass a water service connection, you have to blow the service back to get the cement out of the way. With epoxy, it's so thin, you don't have to do that. But different methods, the same result is you don't have to dig up the water main to do it. Okay, last thing I want to talk about, there'll be a couple of questions, is a backflow prevention and a cross-connection control program. So I'm going to show you a video, but here, this will be on the exam. The cross connection is an actual or potential connection. And the key here is between a potable water system and any other water source through which backflow can occur. So it's the actual point where non-potable water can move back into the potable water system. And it can happen through a couple of methods. One is back pressure. And back pressure means my utility is providing water to the customer, to this house here, at 60 psi or at 900 kPa. And the customer is doing something inside that property to actually create a higher pressure gradient. And that's why we call it back pressure. So the city is supplying 60 psi, the customer has a pump and is creating 70 psi. If I don't stop that somehow mechanically or with an air gap, that 70 psi is going to come back into the municipal system. And that is backflow. The cross connection is the point where that takes place. We never want water that we have treated and sent through the distribution system to come back, ever. So we need a cross connection control program. The other way, and the more common way, is something called back siphonage. So make sure you understand the difference. Back pressure is where the customer has done something to create a higher pressure than the city's grade line. Back siphonage typically is where the city's grade line crashes. God forbid it's because you're doing a flushing program. The city's pressure drops. Water main break, a major fire, something. Power failure and the reservoir drains. And the connection somehow, maybe a taller building, drains back, siphons back into the municipal system. So that is the more common occurrence. Happens every day in water systems all over the world. And that's what we want to do, is protect against that. So how do we do that? Well, we have a variety of means. And I've got a short video that I want to show you because it kind of sums it all up. All right. And as I said, there are several really good videos, but on YouTube. Okay.
Every cross connection poses a different risk based on the probability of the occurrence of the following: a physical connection between the potable water supply and a hazardous substance, the occurrence of backflow conditions, back pressure, or back siphonage, the total failure of the backflow preventer used to isolate the cross connection, and the probability that a non-potable substance is present. Properly selecting a backflow preventer depends on an accurate assessment of the risk of contamination of a potable water supply. The degree of hazard, high to low, must also be identified. Installation criteria and hydraulic conditions must be evaluated by a trained professional before a backflow preventer can be installed. Several organizations set and recommend certain types of methodologies, devices, and assemblies of backflow preventers. Many devices can prevent backflow of contaminants into a water system. The degree of hazard generally determines which of the basic devices that should be used.
So that's an important point. Cross-connection control is a risk-based program. The higher the risk to human health, the higher the level of protection required. So that may show up on the exam. And so we're going to look at a couple of devices from highest protection to lowest.
The most common devices include an air gap, a reduced pressure principal backflow prevention assembly, abbreviated as RP, double check valve backflow prevention assembly, or DCVA, and pressure vacuum breakers, abbreviated as PVB.
So these will be the devices that may show up on the exam. So just be comfortable. And there are some on the slides that I sent you. So you've got the different definitions of them.
Air gap. Air gap is the most effective way to prevent a cross-connection by a separation between a potable water source and a non-potable source because air disrupts the flow. An air gap is not a device. Rather, it is simply physical space. An air gap may look like this, or this. The most common place you see an air gap is in a kitchen and bathroom. There should always be space between the water source and the flood level rim of the receiving vessel. Reduced pressure principal assembly. Reduced pressure principal backflow preventers, or RP, provide maximum protection against back pressure and back siphonage conditions. This device consists of two spring-loaded check valves with a pressure differential relief valve located between the checks. Water flows into the first check valve. As the first check opens, it fills the reduced pressure zone and the top of the diaphragm at the relief valve at a minimum of 2 psig, 13.8 kPa gauge. If there is a back pressure, backflow, or back siphonage, both checks will close and the relief valve will open, venting water to the atmosphere. RP is an assembly designed for both high and low hazard applications. RPs must not be installed in pits where the relief valve could become submerged. RPs should not be installed where platforms, ladders, or lifts are required for access. Double check valve assembly. This assembly consists of two internally loaded independently operating check valves installed as an assembly between two resilient seated shutoff valves and four properly located test cocks. In normal operation, the check valves will open to allow water to pass through. In a back pressure situation, the second check should close. If it doesn't seal properly, the first check will back up the second. The DCVA is only used for low hazard applications. Pressure vacuum breaker. This is a device designed to prevent water from being drawn back into a water supply when the line is closed. The PVB has an internally loaded check valve and an air inlet valve located on the discharge side of the check valve. The PVB is only designed to prevent back siphonage and can be used for internal protection, but not against back pressure. It should be installed where it can be easily field tested and maintained. Assemblies protecting the public water distribution system often have different needs than plumbing code fixture and appliance protection provides. It's more than placing a valve in the pipe. There are detection devices that monitor DCs and RPs that usually include a meter and bypass line for monitoring water loss, but more importantly, safety for fire protection. A double check detector assembly, DCDA, is primarily utilized in fire line installations. Its purpose is to protect the potable water supply line from possible contamination or pollution from the fire system. The reduced pressure detector assembly, RPDA, is typically only used on fire line applications. However, this assembly is intended to protect the potable water supply from fire sprinkler systems that contain chemical additives or can be connected to an auxiliary non-potable water source. There are operational limitations of certain assemblies, and they may not function correctly under certain circumstances. For example, assemblies may discharge more water than building drains are designed to carry, creating flooding issues. The assembly discharge may not be potable water or could be toxic or harmful to sanitary sewer systems. Assemblies may not be submerged. Installers need to avoid vaults and enclosures without venting. Likewise, they should not be located near any corrosive or toxic fumes. Also, backflow protection devices must be secured and protected from vandalism, sabotage, and theft. Vandalism and/or sabotage could result from a disgruntled employee or someone not understanding the importance the backflow preventer represents in protecting public health. And due to the materials often used in backflow preventers, they may also be seen as a target for scrap metal. Plumbers and specialists who install backflow prevention devices should be aware of several factors. Service connectors, for example, will require an expansion tank for thermal expansion. Additionally, backflow preventers produce a system pressure loss and installers should be mindful of plumbing codes and the minimum pressure of 15 psi. Service connection assemblies do not protect the building occupants from internal cross connections. Cross-connection control and backflow prevention program requirements differ by county, parish, region, state, and province. You should check to see who sets the requirements in your area.
So basically, we'll go quickly through the slides just to finish up and hit the high spots that may be on the exam. So they talked about an air gap. On the exam, this is the requirement. So the actual space between the water source and the receptacle, 2 times the pipe diameter. So if this is a 1/4 inch small diameter pipe, then 2 times is 1/2 inch. Oh, except it cannot ever be less than 1 inch. So 1 inch minimum, this space. If this is a 2-inch line coming in, then this needs to be 4. So 2 times the diameter of the inlet, not less than 1. And again, because it's an actual space, it is not an assembly. It protects against both back pressure and back siphonage. So, and will prevent backflow from high or low health hazards. Right, so 2 times the pipe diameter, no less than 1 inch. The Rpa device, right, the reduced pressure device, basically, and to become an assembly, it has to have inlet and outlet shutoff valves, test cocks, as well as 2 independent check valves and the pressure relief valve. This is the highest assembly in terms of protection, right? So it's used when there is a high health risk. But based on how it operates, right, with higher pressure, and these are high head loss devices, right? They take off 8 psi, take off 3 psi as it goes through, creating that differential pressure that allows the relief valve to operate. So you want this to be able to drain and not back up and not flood. And here's an example: the check valve fails, it actually drains. So it's almost like a mechanical air gap. But remember the parts: inlet, outlet valve, 2 independent check valves, relief valve, and then test cocks, these little things here. So it has to be built and sold as an assembly with a nameplate data and a serial number. The DCVA is good against low hazards. So it's very similar to the RP device, except there is no relief valve, right? They're just independent check valves, inlet, outlet, shutoffs, and test cocks. The pressure vacuum breaker is good against low hazards, but back siphonage only, and must be installed 300 millimeters above the highest point. You won't be asked the actual measurement, but this does come up on the exam: a pressure vacuum or an atmospheric vacuum breaker must be installed where? Well, it's on the highest part of the piping, so that it will create that, protect against back siphonage, and then allow and prevent vacuum situations, right? This is an atmospheric, it says pressure vacuum, but for some reason it's an atmospheric breaker. But based on where the shutoff is under normal operating, right, the water comes into the tank, closes the valve. If there is back siphonage, the valve drops, allows air in and into the tank so the tank doesn't collapse. And here's a hose bib breaker, same thing, check valve, preventing water from being pulled back in from the hose. Any good cross-connection control program, you need to know where all of these assemblies and devices are. And typically, a lot of them are on the customer's property. So cities enact bylaws to make sure that the owners keep their devices up to date. The American Water Works Association did a study on new devices and found that less than half of them were actually operational in the first year because they were installed when plumbers were still working and pipe filings and other debris got in and they didn't operate correctly. It is a health hazard insurance type program that cities incorporate into their bylaws to keep the municipal city system safe from hazards, typically generated by the user. Not always, but typically generated by the user. All right, that's it. So basically, to sum up, I've sent you the slides and I've sent you last week's answers. Next week, you'll do the exam, 50 questions. So I can't see it taking more than an hour, but you have 2 hours. And then the following week, week 12, April 14th, you'll get a review of the answers so that you'll have a sense of how you're doing. And then hopefully you've got enough lead time between getting the results of the test, the practice test, and then your actual exam that you're writing. And because this is my last session, I want to thank you all and wish you good luck on your exams for sure. But more importantly, good luck in your overall waterworks career, you know, whether it involves advancement within your utility or moving between utilities. I wish you all the best.
Well, Mike, it has been a wonderful journey. I'd like to thank you so much for giving us your time. Just before we close, I would like to find out, you mentioned how you're going to send the exam. Will you send that through me, or do you want me to send you all the email contacts? So how are we going to do the exam? I was just trying to figure.
I sent you and Val and Ron the exam, both the questions and the answers. So you've got them both. I think Ron was going to jump in and do that, but I'm not 100% sure. And you got a couple of choices. You can give the exam and have all the students send you, you know, their saved copies. It's a Word document too. So
all right.
But you've got, I sent that to you a couple of days ago. Or no, yes, maybe it was this morning. Anyway.
Oh, this morning. Okay, I'll check my mail. I didn't see that one.
Yeah, I think it was this morning.
Yeah. Well, let me thank on behalf of all the participants. I think we have many more persons now than before we started. So if you just turn on your cameras again, I will take this group photo, please. If everyone turns on their cameras. I just need to take this group photos for the operators without borders. They would want to see this.
Man, there are some great smiles in this group.
Yeah.
I wonder if it's probably because the session's over, right?
I'm missing a few. I think there's some people without cameras or something. So,
yeah, I think so.
Yeah.
I think Rashad said he had no camera. So
yeah, Rashad does not have. I don't know Ursuline, Alfred, Josetta McLaurin, Elijah Fauché. Okay, Anderson is trying to log on. Right, great. Okay, so here we go. Cheese. Thank you very much.
Well done.
Okay.
All right, good luck, everyone.
Yeah, and have a good Easter weekend. I think it's a long weekend coming up.
Long weekend, nice.
Okay.
All right, don't eat too much chocolate.
All right then.
All right, take care.
Take care. Thank you, Mike. We'll keep in touch.
For sure.